Okay, today we want to take on Chapter 6. We'll be looking at mixture solubility. We'll be talking about types of mixtures, what affects the solubility of materials in a solution, and we'll be talking about water solutions. The idea of a surfactant, how so works. Now, a compound is a combination of elements that are chemically bonded together. That's the basis for a compound. A mixture, on the other hand, is a combination of materials, elements and or compounds, they can be both, that are not chemically bonded together. They're physically together, but they are not chemically bonded. For example, oxygen, carbon dioxide, nitrogen are all compounds. The atoms are held together by chemical bonds. A mixture, you have a mixture of oxygen, nitrogen, carbon dioxide gases. Each molecule is separate and from the others, and they're all mixed together. Types of mixtures: the homogeneous mixture means the same everywhere in the mixture. A heterogeneous mixture is not the same everywhere in the mixture. A little diagram kind of illustrates that. The homogeneous, you notice the blue and the red squares are the same anywhere in the checkerboard. The heterogeneous, the yellow and the green areas are different depending on where you. A homogeneous mixture, there are no visible boundaries. You can see if you could look at the individual atoms and molecules, you could see them, but you don't see anything. The mixture would be clear. Homogeneous mixtures, such as a sugar solution, once you dissolve it in, the green chemical in the beaker on the left, the aluminum pipe on the right, this is homogeneous. The material is the same anywhere you cut the pipe. Heterogeneous mixture, on the other hand, you can tell the different parts of the mixture. If we're looking at oil droplets in water, you can see the visible boundaries between the water droplets and the droplets. Heterogeneous mixtures, the trail mix sort of thing up in the upper right hand corner, the rock down on the the upper left. The rock down on the lower left is obviously a mixture. You can see the different types of material in this rock. The olive oil or the cooking oil on top of the water is a heterogeneous mixture because it's not the same all the way through. Solutions and colloids. A solution is a type of a homogeneous mixture. You can have solid solutions. For example, gold and silver and copper are mixed together to make jewelry because gold by itself is pretty soft and wouldn't hold up well, but if you put other atoms in there with it, it's pretty sturdy. Gaseous mixture, the air that we breathe is a mixture of oxygen and nitrogen, carbon dioxide for the most part, and so those are equally distributed. A liquid solution, phosphoric acid, water, carbon dioxide for some kind of a soda pop. It's the same throughout the container. So solutions are a type of homogeneous mixture. Colloids, on the other hand, are heterogeneous. Colloids are invisible particles, but they're larger than individual molecules. Milk is a colloid. Butter is a colloid. Marshmallows are a colloid. And a lot of different aerosols in hairspray and other things are colloids. Here's some examples of some colloids. A mixture of two phases of matter, gel and foam, and clouds and milk, solids and liquids. Clouds are air and solids. So if we have fog, we have a colloid. It's a liquid mixed with gas. The air is the gas, the liquid is the water, and it's mixed like this. Smoke is a solid mixed with gas. The particulate matter from the burning of whatever, coal, oil, or whatever is being burned, mixes with the gas, the air, and you get particulate matter and you see a code. Now, if we look at solution terminology, a solution is a small amount of one substance dissolved in a large amount of another substance, which doesn't tell you much. The solute is the material in a solution present in a smaller amount. And the solvent is the material in a solution present in a larger amount. So if we're dissolving a teaspoon of sugar in a gallon of water, the sugar is going to be the solute because it's a smaller amount. The water will be the solvent because it's the larger. Now, what affects solubility? A lot of things determine whether something will dissolve. Okay, keep in mind, solute present in smaller amount, solvent present in larger amount. Solubility depends on the attraction of the solvent to the solute and the attraction of the solute to the solvent. How well do these materials attract to one another? If the solute is not attracted to the solvent, then you get a precipitate or a suspension. You don't get a solution. Here's a suspension. On the left, you can see the bubbles of probably some kind of oil in the water. The oil molecules are not at all attracted to the water molecules, and so they don't dissolve. And the picture on the right, whatever this compound is, it's not soluble. You put it in water and it forms a precipitate. That's the solid material in the water. Now, these factors are affected by electronegativity. And electronegativity is the ability of an atom to attract electrons towards it. Here's a table of electronegativity for some of the smaller atoms. And we'll notice that fluorine on the right has the highest electronegativity. It only goes up to 4. So fluorine has an electronegativity of 4, which means that fluorine is more likely as an atom to attract electrons to itself than would be, say, nitrogen, which has an electronegativity of 3. And carbon has an electronegativity of 2,5. So if we had a carbon-fluorine bond, the fluorine would pull electrons away from the carbon. Now that has some interesting impact. Okay. Electronegativity increases from left to right, lower on the left, higher on the right, and it decreases as you go down the periodic table. The greater the difference in electronegativity, the more ionic the bond. And that's important because the more ionic the bond, the more likely this material would dissolve in water. So in electronegativity situations, you form what's called a polar bond. One atom has a partial or full negative charge, while the other atom has a partial or full positive charge. So you've got positives and negatives more likely to enter the water. Here's some examples of polar bonds. The hydrogen fluoride molecule. The fluorine attracts electrons to itself. It has a 4.0. The hydrogen has an electronegativity of about 1. So it is going to have electrons pulled away from it. So it will be a partial positive. The little Greek letter delta means partial. So it will be partially positive. The fluorine will be partially negative. And water is the same way. Water has oxygen, which is more electronegativity than the hydrogens. So the water molecule, the oxygen, will have a partial negative charge. The hydrogens in the molecule will have partial positives. So we've got partial positives and negatives in the solvent. And if we have partial positives and negatives in the solute, we have a good chance of them dissolving. Now, polar molecules depend on shape and the distribution of things, and we won't go into that, but shape is an important piece of things. Now, we talked about the water and the direction of the water, the way the water molecule is shaped. There's a positive pole and a negative pole because the charges will not cancel each other. Like dissolves like. Polar molecules will dissolve in water, a polar solvent. Water has partial negative and partial positive charges on it. Polar molecules are going to have partial negative and partial positives, so they will interact with one another and more likely dissolve. Nonpolar molecules can't be attracted to polar solvents. The partial negative and partial positive of water is not going to attract a molecule as neutral. Nonpolar molecules dissolve in nonpolar solvents by different mechanisms. An electronegativity chart can tell us what's polar and what's nonpolar. We can look at a molecule and use the electronegativity chart and make a pretty good prediction as to whether it'll dissolve in water. Some nonpolar materials. Ether is nonpolar, doesn't mix with water. Gasoline and oil certainly don't mix with water. Toluene, which is another organic solvent. The inert gases, helium, neon, argon, krypton, xenon, are nonpolar. They've got a complete outer electron shell, and there's no way to distort those electron clouds. Diatomic gases, the same way. Hydrogen, oxygen, nitrogen. These are nonpolar because they have equal electronegativity in the two atoms in the molecule, so they're not going to attract things with one another. Only a certain amount of material will dissolve in water at any given temperature, and there are ways to even predict this. There are tables for it. Energy is needed to break ionic bonds of the solid so the ions can interact with water molecules. Therefore, if you increase the temperature, you'll increase the solubility. There's more energy, breaking more ionic bonds and more actions. Okay, here's a picture of sodium chloride as an ionic bond and how the water will disrupt that, surround the sodium ions and the chloride ions to dissolve them in water. Hydrophilic molecules, ionic molecules, polar groups, all of these will interact with water. Hydrophobic molecules, on the other hand, do not have polar groups to interact with water. Now, a soap molecule is a rather cool thing. It has a hydrophobic tail, so that the tail will interact with the dirt and the oil, and a hydrophilic head, which will interact with the water. So the hydrophilic part will dissolve in water. The hydrophobic tail will attract the dirt and the oils and other stuff to it. And this is how it works. The water molecules interact with the hydrophilic part, and the hydrophobic part surrounds the trapped hydrocarbons and dirt. Biological membranes are the same way. They have hydrophobic and hydrophilic portions to them so that they can interact with water but not dissolve. So we talked about mixtures, we talked about homogeneous and heterogeneous mixtures, about solutions, polar and nonpolar molecules, and surfaces. So there you are, and we'll see you later. Good, take care.